Hey folks, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to tackle different types of word problems that involve chemical equilibrium by going through some class examples. So let's go ahead and get started. For our third class example, we're going to consider the following chemical reaction. Here we have phosphorus pentachloride decomposing in the forward direction to produce phosphorus trichloride and chlorine gas. According to the problem, our equilibrium constant with respect to partial pressure, or Kp for short, is 11.5. And so if a reaction vessel is filled with 2.00 atmosphere of PCl5, which is a reactant, the reactant is going to be allowed to come into equilibrium. In other words, some fraction of the reactant is allowed to decompose to produce these two products. And so our goal is to determine the equilibrium partial pressure of all of the gases that's in the container. So how do we go about and accomplish our goal? Well, from your understanding of quantifying equilibrium in the previous lecture video, the equilibrium partial pressure of a gas pops up in a couple places, and one of those places is the mass action expression with respect to Kp. So let's go ahead and start there. We're going to start this problem off by writing the mass action expression for this chemical reaction. And from there, we're going to see what else we need to address the question. And so Kp is the equilibrium constant with respect to partial pressure of gases. And very similar to all mass action expressions, we're going to basically write the products in the numerator raised to its own coefficient and the reactants in the denominator raised to its own coefficient. So what we have is partial pressure, which is abbreviated as capital P, the partial pressure of this specific substance, PCl3, raised to the first power, because there's a coefficient of 1, times this by the partial pressure of Cl2 raised to the first power, because there's a coefficient of 1, divided by the partial pressure of PCl5, which is our reactant, once again raised to the first power. Now, remember that whenever we're using K, capital K, that implies that all of these substances are at a state of dynamic equilibrium. And so therefore, we're going to go ahead and put in EQ after the parentheses. And so if I zoom out and if we read the problem, the only thing that we can kind of fill in after we wrote the mass action expression is the value for Kp. So we know that Kp is equal to 11.5. However, we don't know what the value is for any of these substances. And if we did, then we would have already figured out the problem. So it looks like we have to rely on another tool or technique, whatever term you want to use, to help us mathematically define what these substances are at equilibrium. And the tool or technique that allows us to do so is the ICE table. And so we're going to go ahead and rewrite the chemical equation. So here we have PCl5, PCl3, and Cl2. And so I'm going to go ahead and put an I, C, and E, which once again represents key phases in the progress of the chemical reaction. The initial state, how the concentration or the partial pressure changes, as well as the equilibrium or final state. Okay. And so I want you guys to notice that I'm creating these lines that kind of separates out these three substances. And so this column is referring to the initial, the change, and the equilibrium concentration for only PCl5, and the list continues. All right, so once again, kind of zooming out, reading through the problem, it looks like this problem only gave us a value for PCl5. And so reading it through, if a reaction vessel is filled with 2.00 atmosphere, so the chemical reaction really hasn't started yet, and therefore this pressure is the initial pressure of this specific substance. So for this problem, we're going to go ahead and put in 2.00 atmosphere as the initial partial pressure. And so once again, if I zoom out, and if you kind of read it through yourself or on your own, you'll notice that there are no initial values that's provided for the products PCl3 and Cl2. There's no mention of it. And so we're going to go ahead and write 0 atmosphere, 0 atmosphere. Okay. All right. So now that we have all of the initial amounts written, let's go ahead and talk about the change. And so looking at the value, the initial values, there's a lot of reactant. And so if there's a lot of reactant, it only makes sense for the forward reaction to proceed. In other words, PCl5, some amount of PCl5 is going to be consumed. And we can go ahead and represent that with a minus and then an X. And so since the coefficient is 1, we need to write a 1 for the change. So it's going to be minus 1x. And so since we're producing products, this is going to be a plus x and a plus x. And to ensure the stoichiometry is represented from the balanced chemical equation, we're simply going to put 1 and 1. Now, for the equilibrium concentration, we're simply going to add down the column. And so, if you recall from the previous lecture video, I plus C equals E. And so when we add down, what we get is simply 2.00 minus x, and then 0 plus 1x is just x, 0 plus 1x, that's just x. So now that we have these mathematical expressions for the equilibrium state for each and every single one of these substances, we're going to go ahead and use all of this and plug it into our mass action expression. And so this term, since it represents PCl5, is going to be plugged into the denominator. And these two x's is going to be plugged in the numerator of where it's written. And so if we kind of plug everything into the mass action expression, what we get is 11.5, which is Kp, equals to x times x raised to the first over 2.00 minus x raised to the first. So anything to the first power, it'll just equal itself. And so we can go ahead and simplify this to x squared over 2.00 minus x, and that equals to 11.5. Let me just reorganize that. So that's 2.00 minus x. All right, and so our goal mathematically is to solve for x. And so looking at the numerator and the denominator, notice that the numerator is raised to the power of 2, but the denominator is not. And so we cannot take the square root of both sides. And so what we have to do to solve for x is just take the denominator and move it to the other side and distribute the 11.5 to it. And so we're going to go ahead and multiply to the other side, giving us 11.5 parentheses 2.00 minus x equals to x squared. And so if we distribute, what we then get is going to be 23.0 minus 11.5, which is equal to x squared. Oops, minus x. Let me erase that real quick. So it's minus 11.5x equals to x squared. And so since there are two different types of x's, so x squared and x, this x is raised to the first power. You cannot really combine this with this. They have different powers. And so when you fall upon this situation, your only option is to really employ the quadratic equation to solve for x. And so to use a quadratic equation, you need to move all of your terms to the side that has the positive x squared. And so here in this case, I'm going to add the 11.5x, and then I'm going to subtract the 23. And so what that gives me is x squared. Well, let me move it. So what I get is x squared plus 11.5x minus 23.0. All of this is equal to 0. And so once your algebraic expression equals to 0, you can now use the quadratic equation to solve for x. And so the quadratic equation is going to be negative b. I'll go ahead and write it over here. So here we have quadratic equation. So that's negative b plus minus the square root of b squared minus 4 times a times c over 2a. And so the a, b's, and c's represents the coefficient that's in front of each term. And so the coefficient in front of x squared is 1, so a is equal to 1. The coefficient in front of this x is 11.5, so b is equal to 11.5. And c is going to be negative 23.0. And so we're now going to go ahead and plug it in to the quadratic equation and then simplify that quadratic equation until we get 2 roots or 2 answers. And so I have negative b, so that's a negative 11.5. Let me zoom in here. It's easier for me to write. So negative 11.5 plus minus square root of 11.5 squared minus 4 times 1 times c, which is negative 23, over 2 times 1. Okay? So I've basically substituted all values of a, b, and c with what they are based on this quadratic expression. All right, and so our next step is to simplify this. And so what I'm going to do is I'm going to plug everything that's inside the square root first in my calculator. So give me a second here. I have 11.5 squared, and so feel free to follow along if you want. So 11.5 squared minus 4 times 1 times negative 23.0. And so the value that I get is going to be 224.25. Okay. And then 2 times 1 is simply 2. And so if I take the square root of that, I get negative 11.5 plus minus 14. So in terms of sig figs, I'll just carry 3 sig figs. But for now, so I'll put in 14.97 for accuracy, but for precision, I'm going to put a horizontal line at the top, indicating or reminding me that there's only really 3 sig figs that I'm going to consider. Okay. Everything is divided by 2. So once you guys have reduced your, actually let me move this down here. Okay. So after you guys have reduced everything in the square root, notice how there is a plus form and a minus form. And so we're going to create 2 fractions or 2 expressions in which we have the positive form of the root and we have the negative form of the root. So we have negative 11.5 plus 14.97 over 2. And then here we have negative 11.5 minus 14.97 over 2. Okay, and I'm going to put that horizontal line over the 9, just a reminder for sig figs. So if these are our 2 roots, our 2 values for x, we're going to go ahead and reduce these values. So in my calculator, I'm going to put in negative 11.5 plus 14.97 divided by 2. And then this is going to give me a value of 1.735. And so since I have 3 sig figs, I'm just going to go ahead and round this to 1.74. Okay? So this is going to be one value for x. And if I reduce this, I have negative 11.5 minus 14.97 divided by 2, I get a value that is negative 13.24. And so if I keep 3 sig figs, I get another x value of negative 13.2. And so that's great. We're able to solve for x, but unfortunately, we have 2 values of x. And so which of these 2 values is the true value that we're going to plug in to obtain our equilibrium concentration? Well, if you guys think about this, could we have an x value that's negative? Okay, so negative 13.2. So if you imagine that I plug in negative 13.2 for x in our in the E part of the ice table, could we ever have a negative value for atmospheres or for amount of substance? And the answer is no. And so it doesn't make sense for us to choose negative 13.2 as the true value of x simply because a substance cannot be negative, right? So our substance will always have to be positive, and it must be within the correct scope or the correct range. Otherwise, it just wouldn't be feasible. And so let me go ahead and cross this off. Okay, so this is not our true value, so I'm actually okay. So I'm going to go ahead and cross this off. And I'll just put in a note that says x cannot be negative. Okay. Right. And so remember, x is going to represent that unknown, that amount that's changing. And so here in this case, we're going to keep this value, but we're going to see if 1.74 is within a reasonable range or a reasonable scope. And so if I'm going to see here, I'm actually just going to copy and paste this real quick, so give me a second. Okay. Okay. All right. And so now that I have copied my ice table so that we can all just see one screen, notice that the highest amount of a substance that we have is 2.00 atmosphere. And so 2.00 is greater than 1.74. And so since 1.74 is less than this original value, the initial value, the change, the minus x, that it represents is feasible. If this number is 3.0, even though it's positive, that can't occur. So it must be less than the initial amount. Okay. So now that I have a value of x, I'm going to go ahead and determine the equilibrium partial pressure for all of these gases. And so for PCl3, let me go ahead and, so the partial pressure of PCl3 at equilibrium is defined as x, which is 1.74. And so now that I'm describing that the value of x is the partial pressure, I need to put in my unit, which is atmosphere. So please don't forget that. And so the equilibrium partial pressure of Cl2 is also defined as x, which is going to be 1.74 atmosphere. And finally, the partial pressure for PCl5, which is our reactant at equilibrium, is expressed as 2.00 minus x. And so we're simply going to plug in x, which is 2.00 minus 1.74. And what we're going to get, let me just move this a little bit to the left. Okay. So 2.00 minus 1.74 is going to be 0.26 atmosphere. Okay. And so overall, we've now solved for the equilibrium partial pressure for all of the gases that's present in the container. Okay. And so this is a little bit different than the problem that we've seen in a prior lecture video because we've implemented the quadratic equation. And that's really only the case when you cannot square root both the numerator and the denominator. Like if you guys can't take the root of both the numerator and the denominator, then you might have to employ the quadratic equation. And so we're going to see another variation of this in just a second. There's a way to actually streamline our work. So there's a way in which we don't have to use the quadratic equation to solve for the value of x. And that condition is very specific, and we'll see that in the next problem that we do. But one last thing before I move on to the fourth class example, notice that the Kp is 11.5. And so this is the scenario in which, so Kp is 11.5. So this is the scenario in which Kp is greater than 1. And if you recall, if the Kp value is, or if the equilibrium constant, doesn't matter if it's Kc or Kp, if that's far, far greater than 1, then we know that the amount of product at equilibrium is going to be greater than the amount of reactant at equilibrium. And so looking at our values, these two are products, and the values are much higher than the reactant. And so therefore, we've these values kind of substantiate the concept that we learned a few lecture videos. And if you guys wanted to create a concentration versus time graph for when your equilibrium constant is far, far greater than 1, we can go ahead and put in the concentration on the y-axis and time on the x-axis. And so since the equilibrium concentration of the product is greater than the equilibrium concentration of the reactant, we're just going to go ahead and put two lines, one on top of each other. Make sure to give it some space. So this is going to represent products at equilibrium, and then it's going to represent reactants at equilibrium. And we know that at the start of the chemical reaction, we have a lot of reactants. And so we're just going to go ahead and draw a curve, kind of connect that. And we know at the very start of the chemical reaction, we have 0 products. And so we're going to go ahead and just connect those 2 points. And that's going to be the graph for concentration versus time for products and reactants. Okay. All right. So let's go ahead and look at another problem. And so I mentioned before that if you get into the scenario where you can't get rid of the exponent because the exponent is only on one side of the fraction, there's a way in which you guys can bypass, so to speak, the use of the quadratic equation. And we're going to go ahead and see it here. So let's go ahead and check out this problem. So for example number 4, we have another chemical reaction in which 2 moles of water vapor is going to decompose in the forward direction to produce 2 moles of hydrogen gas and 1 mole of oxygen gas. And so at this specific temperature, the equilibrium constant with respect to concentration, so Kc, is equal to 7.3 times 10 to the negative 18. So here, if the initial concentration of H2O is 0.250 molar, what's the equilibrium concentration for each substance? And so once again, we're looking for the equilibrium concentration for each of the substance that's found in the chemical equation. And very similar to the previous example, to accomplish our goal, we need to write the mass action expression, because the mass action expression will help us define the equilibrium concentration for each and every single one of these substances. And so Kc is going to equal to products of reactants raised to their own power. So here in this case, here we have the bracket, meaning the concentration of H2 gas. And since it's since there's a coefficient of 2, this is going to be raised to the second power. And we're going to multiply this by the concentration of oxygen gas. And since there's a coefficient of 1, then this is going to be raised to the first power. And then we're going to go ahead and divide that so that we have the concentration of H2O gas. And that's going to be raised to the second power because we have a coefficient of 2. Now, like what I mentioned before in the previous problem, if we're using the equilibrium constant, whether it's Kc or Kp, then it's basically describing that every single one of these substances is at chemical equilibrium. So I'm just going to go ahead and put an EQ to remind myself that these are equilibrium concentrations. And so the only thing that the problem gave me is that Kc is 7.3 times 10 to the negative 18 power. However, the problem did not state any of the equilibrium concentrations. And so we need some type of mathematical expression that will help us define what each of these substances, or that will help us define what the equilibrium concentration of these substances are. And to do that, we need to develop an ice table. Okay. So in developing the ice table, I'm going to go ahead and rewrite the chemical equation. Okay. And then I'm going to create a table that would separate out every single one of these substances. Okay. Apologize, this is going to take a second. All right. So here we have 3 columns, one for water, one for hydrogen gas, and one for oxygen gas. And so let's go ahead and look at the initial concentrations. So we already used this value, that's great, and the initial concentration is 0.250 for H2O. And it didn't really state the initial concentrations for hydrogen or oxygen gas, so we're going to assume that it's 0. So here I have 0.250 molar concentration, and then I have a 0 molar concentration and 0 molar concentration. So looking at the initial concentrations for all 3 of these substances, notice that I have an amount for the reactant and none for the product. And so as the reaction progresses, it makes sense for the reaction to progress in the forward direction. In other words, we're going to consume the reactant that's already present to produce product until such time that the chemical reaction has reached a state of chemical equilibrium. And so since I'm consuming reactant, I'm going to put minus X, and then since I'm producing product, I'm going to put in plus X and plus X. Now, to ensure the stoichiometry, I'm going to bring that 2 down, and I'm going to put this 2 down, and then I'm going to put this 1 down. Okay. And to determine the equilibrium concentration, the mathematical expression for the equilibrium concentration, I'm simply going to add down the column. I'm going to add I and C. And so what I get is 0.250 minus 2x plus 2x, or simply 2x, plus 1x, or simply x. And so these expressions, if you will, we'll define the equilibrium concentration of each and every single one of those substances. So very similar to the previous problem, I'm going to take this expression and plug it in wherever I see water. So that 0.250 minus 2x represents water. And I'm going to take this 2x and I'm going to plug it into H2. I'm going to plug this guy into O2. All right. And so if I do that, I'm going to get 7.3 times 10 to the negative 18, which is my value for Kc. And then that's going to equal to 2x. Now, don't forget this power, right? Don't forget the powers. Simple mistakes can be made that will give you wrong answers if you guys don't forget the power when you carry it over or when you rewrite it in your work. So not only is it 2x, but it's 2x squared times this by x to the first over, here in this case, it's going to be parentheses 0.250 minus 2x. And then it's going to be raised to the second power. Okay. All right, so let's go ahead and simplify this. So what we get is 7.3 times 10 to the negative 18. That's going to equal to, so we're going to go ahead and distribute it to every single one of those terms. So 2 squared is 4, and then x squared is x squared, times this by x. Okay, and so here we have 0.250 minus 2x squared. And then once again, if we combine the terms, you know what, let me just duplicate this. Just want to show my work. Then if we combine the numerator, what we get is 4x to the third. Okay? And so this is a third root, or this is raising the exponent to the power of 3. And so unless you've gone through an advanced algebra course, you guys will probably know how to figure out the roots if you have something that's cubed. But for the most part, this is a little bit difficult to work with. And so you also have an x squared term. You also have something that's raised to the power of 2 in the denominator. So this looks very, very messy. However, we can actually simplify this whole expression if we kind of pay attention to what the Kc value is. And so if you recall, I'll go ahead and put it off to the side over here. Kc, if the Kc value is far, far less than 1, then that means that at equilibrium, the concentration of reactants is far, far greater than the concentration of the products. And it is this concept that will allow us to approximate our denominator. And so let's think about this. If the concentration of the reactants is much, much greater than the products, then did a lot of reactants get converted into products? And the answer is no. And so since there's not a lot of reactants that's being converted into products, then what we can do is approximate the change to be very close to 0. Okay? So this is the situation in which we can approximate the change to equal to 0 only for the reactant. Okay? So any amount that gets consumed in the reactant side is negligible. However, we're not going to ignore the x's in the product side, because if you're looking at this, anything that's greater than 0 is significant, right? And so here, if this change is very small, it's not really going to affect the value, the initial concentration. And so that's why we can go ahead and approximate this change to be 0. And if we apply that trick, if you will, it'll allow us to solve this expression a lot easier and a lot faster. And we don't have to use some fancy technique, some fancy math technique to solve for the root, to solve for x. All right, and so we're going to go ahead and take this 2x and approximate it to 0. Okay, and so I'm just going to put an arrow there for the rationale. And so if I do that, I get 7.3 times 10 to the negative 18 equals to 4x to the third over 0.250 squared. And so by approximating that x in the denominator, I've really made this mathematical expression very easy to solve. And so I'm just going to go ahead and multiply this to the other side. And I get 7.3 times 10 to the negative 18, parentheses 0.250 squared, that's equal to 4x cubed. Okay. So if I plug that into my calculator, so 7.3 times 10 to the negative 18 times that by 0.250 squared, that's going to give me a value of 2 sig figs here, so 4.6, so I'm rounding up. And in the calculator it says 4.5625, but since I'm only recording 2 sig figs, I'm going to go ahead and round up to 4.6 times 10 to the negative 19. Okay. And so I'm going to go ahead and divide both sides by 4. Okay. And I get 1.1 times 10 to the negative 19. And so from here, let me just clean up my writing a little bit. I'm going to go ahead and take the third root of both sides. And so in your calculator, if you don't know how to type in a third root, you can go ahead and put in parentheses 1.1 times 10 to the negative 19, and then put that caret sign, and then put in another parentheses 1 divided by 3. Okay, so that's the same thing as a third root. Okay. So that's going to cancel that term. And so what I get is, what I get is 4.8 times 10 to the negative 7. So this is going to be my value for x. So let's think about the answer for x with respect to the concept. And so is this right for us to ignore the 2x? Okay, so let me put that here. Okay, let me erase all of this. Okay. All right. So let's think about this concept. Was it right for us to ignore this minus 2x? Well, 4.8 times 10 to the negative 7, that's 6 zeros. So 1, 2, 3, 4, 5, 6. And then that's the seventh place. And then so it's going to be, oh man, so 0.1, 2, 3, 4, 5, 6, 4, 8. So this is a very, very, very small number. So if you plug it into x, will it change the value 0.250 significantly? Okay. And so let's go ahead and check that out. So if we want to calculate the equilibrium concentration of water, which is our reactant, 0.250 minus 2x, so that's going to be 0.250 minus 2 times 4.8 times 10 to the negative 7. Okay. Okay. And so what I get is 0.2499999, and the list continues. Or at some point there was a 3. Sorry. So 0.24, and then 4 nines, and then a 0, and a 3, and a 0. And so if you express this to the correct number of sig figs, it's still going to be 0.250 molar. Okay? So this is telling you that there really is no significant change to the concentration of the reactant, which justifies our approximation in this step. Okay, so this is the proof of our justification. However, if we calculate the equilibrium concentration for both H2 and O2, anything above 0 molar is significant. So the concentration of H2 is defined as 2x, which is going to be 2 times 4.8 times 10 to the negative 7. So let me plug that in. So 2 times 4.8 times 10 to the negative 7, which is going to be 9.6 times 10 to the negative 7. Okay. So 9.6 times 10 to the negative 7 is significantly greater than 0, but obviously it's still times 10 to the negative 7, so it's not really a lot. But compared to 0, it's much greater than it. Oh. And so this is going to be the equilibrium concentration of H2, and for O2, the equilibrium concentration is defined as X, or simply 4.8 times 10 to the negative 7 molar. All right. So overall, everything that I'm highlighting here is going to represent the equilibrium concentration of these substances. And so let's go ahead and think about the concept once again, see if our numbers match up with the concept behind Kc. So the Kc for this problem is, what was the case? Oh, 7.3 times 10 to the negative 18. So it's 7.3 times 10 to the negative 18. So this is telling us that with 1 as our reference point, Kc is far, far less than 1. And if Kc is far, far less than 1, then the concentration of the reactants is going to be much, much greater than the concentration of the products. And so did our calculation reflect that? Yes, it did. This H2O, which is a reactant to this 0.250, is going to be much, much greater than these values. And so the concept, the math does prove the concept and vice versa. So if I wanted to create a concentration versus time graph that represents Kc that's far, far less than 1, notice that reactants is greater than products, so I'm going to have 2 lines. So this is going to represent the reactants this time. And then this line, this line is going to represent products. Now, if you recall, the concentration of the reactants is 100%, so we're up here. So we're just going to go ahead and connect the reactants to the reactants. So we're going to connect this dot to this line. And if you recall, at the initial time period, the amount of products that we had is 0%. And so I'm going to go ahead and connect that point to this line. And so this is what the concentration versus time graph of reactants and products looks like when Kc is far, far less than 1. All right. Cool. So let's go ahead and move on to the next problem. Let's go ahead and look at another scenario that you guys might come across when dealing with word problems involving chemical equilibrium. So here we're going to consider the following reaction. This is our 5th example. Here we have H2 gas, iodine gas, and 2 moles of hydrogen iodide at this specific temperature. A container with a volume of 1.5 liters initially contains this amount of moles of hydrogen gas, this amount of moles of iodine gas, and this amount of moles of HI gas. When an equilibrium was established, the concentration of iodine gas was this amount. And so from the information that's given, we're going to determine the equilibrium constant, Kc for the reaction. And so this time our goal is to not find the equilibrium concentrations per se. Our main goal is to figure out the equilibrium constant Kc. So to determine the value for Kc, we need to be able to write the mass action expression. So Kc is a ratio of products to reactants raised to their own power, or raised to their own coefficient, I apologize. So I have the concentration of HI. In this case, it's going to be raised to the 2nd power because I have a coefficient of 2. Divided by the concentration of H2, hydrogen gas raised to the 1st power, times this by concentration of I2 raised to the 1st power. Okay, once again, there's a 1, coefficient of 1, coefficient of 1, coefficient of 2. So that's where I'm getting those powers from. And so since we're using the equilibrium constant Kc, we know that all of these concentrations reflect equilibrium concentrations. Okay. And so it looks like from our mass action expression, for us to determine the equilibrium constant Kc, we need to know the equilibrium concentration for all of these substances. And our ICE table is going to give us that mathematical expression that we need to quantify these concentrations at equilibrium, as you guys have seen in prior examples. And so to build my ice table, I'm going to once again rewrite just the backbone of my chemical reaction. Okay. So feel free to kind of fast forward until that ice table is built. So it's going to just take me some time. Oops. All right. So now that my ice table is built, remember that each column represents the substance that's right above it. Okay. And so let's go ahead and fill in our initial concentrations. And so here we have moles, units of moles, and we know concentration needs to be in molarity. And so therefore we need to take this value and divide it by the total volume of the container. So I'm just going to go ahead and put this off to the side for now. So here I have the initial concentration of, what was this one? H2. Oh, too many things moving. So this I is going to represent the initial concentration. So that's going to be 0.00623 or 6.23 times 10 to the negative 3 moles over the total volume is 1.5 liters. Okay. And so if I plug that value, or if I plug that into my calculator, so 6.23 times 10 to the negative 3, divide this by 1.5, that's going to give me a value of 4.15. So that's going to be, actually let me just move this to the left. So that's going to be 4.15 times 10 to the negative 3 molar. Okay. And so the initial concentration of I2, okay, so iodine gas is 0.00414 or 4.14 times 10 to the negative 3. 0.0414 moles for every 1.50 liters. Okay, let me plug that into my calculator. So I have 4.14 times 10 to the negative 3. Divide that by 1.50. And then that's going to give me 2.76 times 10 to the negative 3 molar. And so my initial concentration of HI is going to be 0.0244 or 2.44 times 10 to the negative 2 moles for every 1.50 liters. So 0.0244 divided by 1.5, that's going to give me 1.63 times 10 to the negative 2 molar. Okay. So I went ahead and calculated the initial concentrations for each and every single one of these substances, and I'm going to go ahead and plug that into my ice table. So here I'm going to put in 4.15 times 10 to the negative 3 molar. This is going to be 2.76 times 10 to the negative 3 molar. And this is going to be 1.63 times 10 to the negative 2 molar. Okay. All right. So looking at our initial concentrations, I want you guys to notice that for this specific example, the amount of products that we have is much greater than the amount of reactants. If you guys are just talking about the numbers, all right, so times 10 to the negative 2 is bigger than times 10 to the negative 3. And so for this chemical reaction, it looks like the reverse reaction will occur. So there's going to be a net shift in the reverse direction just because we have more of the product than the reactant. So we have less of the reactants. There's actually another way to understand this point, and let's go ahead and talk about this last value here. And so when equilibrium was established, the concentration of I2 gas was 0.00328. So that's telling you that the equilibrium concentration for I2, if I convert it to scientific notation, is 3.28 times 10 to the negative 3. So all I'm doing is moving this place 3 times to the right. And so remember that the equilibrium concentration is kind of like the final state. And so the beginning amount of iodine is 2.76, but at the very end it was 3.28. And so we have an increase in concentration of I2. So the only way that this value can increase is if there is a net movement of the chemical reaction towards the side of the reactants. And so this is kind of like a secondary confirmation that this reaction will move to the left instead of the right. Okay? And so what this means is that the change is going to be minus 2x plus x plus x. And so the equilibrium concentration here, I should have given it some more space, that's okay. So the equilibrium expression for each and every single one of these substances is 4.15 times 10 to the negative 3 plus x, 2.76 times 10 to the negative 3 plus x, and finally 1.63 times 10 to the negative 2 minus 2x. Okay, and so let me just put a note over here that this is the equilibrium concentration of I2. Okay. And so since the problem gave me the equilibrium concentration for one of my substances, I can actually determine what the value of x is without doing all this crazy madness that you guys have seen in the previous class examples. And so here we have 2.76 times 10 to the negative 3 plus x equals to 3.28 times 10 to the negative 3. So remember that this is the equilibrium concentration for I2, and therefore this expression from the ICE table must equal this value. And so to solve for this, I'm just going to simply subtract 2.76 times 10 to the negative 3 to the other side. And so the value of my change, the value of my x, give me a second here, so 3.28 times 10 to the negative 3 minus 2.76 times 10 to the negative 3. Okay, so the value for x is going to be 5.20 times 10 to the negative 4. Okay. So that's awesome. Once I've figured out my value of x, I can go ahead and plug in this value of x everywhere where I see x for the equilibrium concentration. And once I've figured out the equilibrium concentration for each and every single one of these substances, I can then go ahead and plug it into my mass action expression, which allows me to solve for Kc. Okay. And so I'm going to go ahead and start out by writing the equilibrium concentration of I2. This is already given to us in the problem. And that's going to be 3.28 times 10 to the negative 3 molar. Okay. And so the equilibrium concentration of H2 is expressed as 4.15 times 10 to the negative 3 plus x, which is going to be 4.15 times 10 to the negative 3 plus 5.20 times 10 to the negative 4. Okay. And so I just grabbed that from this expression. And finally for HI, it's going to be this expression over here. Actually, let me just plug this in real quick. So I have 4.15 times 10 to the negative 3 plus 5.20 times 10 to the negative 4. So what I'll get is 4.67 times 10 to the negative 3 molar. Okay? So this is going to be the equilibrium concentration for hydrogen gas. And so to determine the equilibrium concentration for hydrogen iodide, that expression is going to be 1.63 times 10 to the negative 2 minus 2x. So 1.63 times 10 to the negative 2 minus 2x. So that's going to be 1.63 times 10 to the negative 2 minus 2 times 5.20 times 10 to the negative 4, since that was the value for x. So I'm going to go ahead and plug this to my calculator. So 1.63 times 10 to the negative 2 minus 2 times 5.20 times 10 to the negative 4. And what I get here is 1.53, if I round to the correct number of sig figs, times 10 to the negative 2 molar. Okay, so this is going to be my equilibrium concentration for HI. So now that I have my equilibrium concentrations, I'm now going to go ahead and plug all of these numbers into my mass action expression to finally solve for Kc. So I'm going to go ahead and plug this guy here, this guy up here, and this guy right there. Okay. And so the value of my equilibrium constant Kc is equal to 1.53 times 10 to the negative 2 squared over 4.67 times 10 to the negative 3 times that by 3.28 times 10 to the negative 3. Okay. So I'm going to go ahead and punch that into my calculator, which will finally give me the answer that I'm originally looking for. So I'm going to square the numerator, and then I'm going to divide this by 4.67 times 10 to the negative 3, and 3.28 times 10 to the negative 3. And so the value that I get is going to be 15.2. Okay. All right. And so this is going to be my final answer. And so notice that Kc is greater than 1. And so when Kc is greater than 1, the concentration of products should be greater than the concentration of reactants at equilibrium. It's kind of messy over here, so maybe I'll rewrite that. Okay. So the concentration of products at equilibrium is greater than the concentration of the reactants at equilibrium. And so do our values reflect that concept? And the answer is yes. Times 10 to the negative 2, which is this is our product, is greater than times 10 to the negative 3. These are our reactants. Okay. So if you want, you can build your concentration versus time graph just to kind of visualize the progress of the chemical reaction. And so here we have products, products, reactants, and this is going to be our kind of starting point-ish, and there we go. Okay. All right. So that pretty much finishes it for this problem. This is a little bit different than what we've seen in prior class examples in a couple ways. One, we have initial concentrations present for all three substances. We have to calculate those initial concentrations, and we have to understand that this reaction is kind of shifting to the left. It's kind of favoring the production of reactants just by a little bit. But once the chemical system has reached a state of equilibrium, the amount of products present is still greater than the amount of reactants. And so it makes sense that the Kc value is still greater than 1. Cool. So let's go ahead and work through our last class example. And this one is a long one because there's two parts to this. And so this problem is an offshoot in one of your problems in your worksheet. And so this last example it's pretty significant because we're going to finally see how the partial pressure of the reactant is going to be converted using PV equals nRT. And we'll go through that when we work through this problem. So let's start. So for our sixth and last class example for this chapter is a reaction that involves carbon monoxide, water vapor to produce hydrogen gas and carbon dioxide. And so we have 125 grams of water with an equal molar amount of carbon monoxide placed in 10 liters. So this is the volume of our reaction vessel. So based on all of this information, what is the equilibrium constant in Kp value? And so it was determined that the equilibrium partial pressure of carbon monoxide is 9.80 atmosphere. So in a sense, just by reading this the first part of this problem, it's very similar to how we would tackle solving for Kc here. So we just need to determine the equilibrium concentrations. And we can do that since one of the equilibrium concentrations is provided for us. Okay? So that's a common thread between problem 5 and problem 6. So the only difference is that this time the value represents the equilibrium partial pressure, which is 9.80 atmosphere. And so what we're looking for is the equilibrium constant Kp. However, if you read at the very beginning of the problem, we're given mass of water, and it's telling us that we have an equal molar amount of carbon monoxide. And so let's go ahead and work through this problem. And so if we have 125 grams of water, and if we want something expressed in moles, then that means we have to convert grams into moles, right? And so the way to do that is to figure out the molar mass of water. And you guys can look up the atomic masses of each and every single one of those elements. So I have 2 hydrogens, and I'm going to multiply that by 1.008 grams per mole. So that's coming, this value is coming from the periodic table. The 1.008 is coming from the periodic table. And then oxygen, we only have 1 of it. Multiply that by 15.999. And so ideally, I would like you guys to record 3 places after the decimal when calculating molar mass. And so we're just going to add all of this stuff after we multiply across. And what we get is going to be 18.015 grams per mole. All right, and so since we want to cancel grams, we want to put grams at the bottom. And so we can go ahead and rewrite this as 18.015 grams per mole. And I can extend this line further to the left. This demonstrates that wherever I place grams on my dimensional analysis, this number follows. And so I'm going to put grams of water at the bottom, so therefore 18.015 must be placed in the denominator. And then what goes in the numerator is just 1, which is 1 mole. And so I'm going to go ahead and type this into my calculator. Let's see here. So what I get is 6.939 moles of water. And so remember that this problem is telling me that I have an equal molar amount of carbon monoxide. And so the molarity of water is equal to the molarity of carbon monoxide. And so right now I just have units of mole, but I can convert moles into molarity by dividing it by volume. And so the volume is 10 liters. Oops. And so what we get is 0.6939. So it's going to be 0.6939 molar. So this is the molar concentration for both water and carbon monoxide. And so once again, reading this part, this is describing the initial amounts of carbon monoxide and water. So I can go ahead and build an ice table. So here I have carbon monoxide plus water producing, I can't remember, H2 and CO2. Okay. H2 and CO2. And so I'm going to go ahead and build an ice table. Okay. And before we plug in these values, I want you guys to note that we're trying to solve for the equilibrium constant Kp. And so while I'm still setting things up, I'm just going to go ahead and set up the mass action expression. So Kp is equal to the partial pressure of H2 gas raised to the first power times this by the partial pressure of CO2 gas raised to the first power, partial pressure of CO raised to the first power times this by the partial pressure of H2O raised to the first power. And let's see here. The problem also stated that the partial pressure of carbon monoxide is 9.80 atmosphere. And so, what was it? Carbon monoxide, so that's CO. So that's telling me that the equilibrium partial pressure is 9.80 atmosphere. Okay. And so if you plug in 0.6939 molar without paying attention to the units, you'll see that there is going to be a difference. Okay, so molarity is not the same thing as atmospheric pressure. And since we're trying to solve for Kp, that means all of these substances are in atmosphere units. And so we need to somehow convert the concentration into units of atmosphere. And the only way to do that is to use the ideal gas law. So if you recall, pressure times volume is equal to N times R times T. And so if we divide V over to the other side, this section right here becomes molarity. Okay. So we can determine the partial pressure of water by taking the concentration, which is 0.6939, and multiply it by 0.0821, and the temperature needs to be in Kelvin. So this is actually the first time that we've used the temperature in our problem. So other problems we've ignored it because temperature is not really changing for the reaction system, so it's just like a constant. So here in this case we have 275 plus 273.15. And then that's going to give us 548.15 Kelvin. And so I'm going to go ahead and put in 548.15 Kelvin. Okay. And so there's a reason why I put in the partial pressure of H2O is equal to partial pressure of CO, because they're basically the same values. And it was said here as well, right? Water equals CO. So I'm going to take this value 0.6939 and multiply by 0.0821 times that by 548.15. And the value that I get, is going to be 31.23. And so I'm going to go ahead and just keep 3 sig figs. So I'm just going to leave the 3 here for accuracy, but I'm going to put that horizontal line just to remind myself what the precision is. So it's 31.2. And the unit is going to be atmosphere, because we solved for the pressure, P. So here I have 31.23 atmosphere, 31.23 atmosphere. And the problem didn't really give us an initial amount of products, so I'm just going to put 0 and 0. And so looking at the initial partial pressure, since we have reactant present, it feels like the reaction is going to go in the forward direction before the chemical reaction has reached a state of chemical equilibrium. In other words, we're going to consume reactants and produce product. So this is going to be minus x, plus x, and plus x. The coefficient is 1, 1, 1, 1, 1. And so here, the equilibrium concentration, or sorry, the equilibrium, the expression for the equilibrium concentration of CO is 31.23 minus x, 31.23 minus x, x, and x. And so remember, the goal for part A is to figure out the equilibrium constant with respect to partial pressure. And so what we need to do is figure out what the equilibrium partial pressure is for each and every single one of these substances. Now, the problem told us that this is the equilibrium partial pressure of CO. And so that must mean that 31.23 equals to 9, minus x is going to equal to 9.80 atmosphere. Okay, so once again, the idea is that if this is the partial pressure of carbon monoxide at equilibrium, and if this is the mathematical expression for the partial pressure of carbon monoxide at equilibrium, then both of these must be equal to each other. And so if I solve for x, so I'm just going to go ahead and do this really quickly on my calculator. 9.80 minus 31.23. That's going to give us, and then if I divide that -1, that's going to give me 21.43, or just 21.4. And so it looks like the value of x is 21.4. So therefore, the partial pressure of H2 at equilibrium is going to be 21.4. The partial pressure of CO2 at equilibrium is going to be 21.4. The partial pressure of carbon monoxide, this was already given to us, that's going to be 9.80. And the partial pressure of H2O, at equilibrium, it's also going to be 9.80 if you do the math. right? So notice that this is the same as this. So therefore, if you plug in this value, you'll get this as your answer. And so all of these units are in atmosphere. Okay. And so now that we have the, now that we have the values of each of these substances at equilibrium, we're just going to go ahead and plug it into this mass action expression. And everything is raised to the first power. So what we have is Kp is equal to 21.4 times this by 21.4 over 9.8 times 9.8. Okay. So let's go ahead and plug that in. And so my Kp value is going to be 4.77. Okay. All right. So that's pretty much it for part A of number 6. It's very, very similar to what we kind of did in the 5th example, where we utilized the equilibrium concentration or partial pressure of one of the substances to figure out the value of X. The only difference in the technique that we used here in this example is being able to convert concentration into partial pressure. And so what prompted us to convert molarity into partial pressure is because the equilibrium is in partial pressure units or atmosphere units, not concentration units. And so therefore, the initial amounts must be in atmosphere, not concentration units. So this last part, this is actually really long. I'm going to go ahead and just show my work on this PowerPoint, so you guys will have it on Canvas. But I'm not going to show my work on video, just because this problem is long. It's a quadratic, and there's a couple of foils and all of this stuff. So just read through my work. If you guys have any questions, you guys can go ahead and ask me during office hours. But for now, I'm going to go ahead and end this lecture video here. All right, guys, so we're done with this chapter. We're going to move on to acids and bases. See ya.